Let's get going. So do you? I'll ask David to confirm that he's willing to have this video recorded.
Yes, absolutely.
Cool. All right. So welcome everyone to the first invited talk at ANTS, and it's my great pleasure to introduce David Harvey. I'm delighted that he accepted this invitation to speak. So David's an associate professor at the University of New South Wales in Sydney, Australia. His PhD was with Barry Mazur at Harvard, and he's extremely successful in his career, and a couple of honours in particular. He's been awarded an Australian Research Council Future Fellowship, which is a pretty prestigious thing, and he also won the 2019 Australian Mathematical Society Research Medal. So David, take it away.
All right, thanks very much, Stephen. So good morning, or afternoon, or evening, or whatever it is. So welcome. This is my basement in Sydney. As we've just noted, I don't have any of those yellow books in the background, but that's okay. I'd like to thank Steve and Drew and the committee for this invitation. I was very excited to be able to come to New Zealand because it's unusual that ANTS is in such a convenient time zone. So that hasn't worked out so well, unfortunately. Everything in this talk is joint work with Joris van der Hoeven. I've been working with Joris for a number of years on mainly integer and polynomial multiplication. Last year we announced some new complexity results for these problems, and that's mainly what I'll be talking about today. So let's see if I can go to the next slide. Here we go. Yeah. So first, I want to get this out of the way, as Steve has already alluded to. So many of you will know there's and in an email to the program committee a few weeks ago, Stephen said, among other things, that New Zealand is the, and I quote this precisely, best country in the world. Now when he said this, I went away and thought about this and looked into it a bit, did some research, crunched the numbers, and I discovered that in fact he's correct. New Zealand is in fact the best country in the world, and here is the data to show this. So as you can see, on all the key metrics, New Zealand does come out in front. I have to say that last line is looking a little bit shaky at the moment. Things are not looking so good in Melbourne. I suppose better than most places in the world, but inching upwards. I left out the line with the sporting statistics because I thought that wouldn't be fair. Anyway, let's move on to some mathematics. So there's two problems I want to discuss today. The first being integer multiplication. So here I'm looking at the cost of multiplying n digit integers. I'm usually thinking n being the number of bits in these integers, but you can work in any fixed base you like. So the same results work for decimal or any other base. And when I say cost, so technically I'm working in a multi-tape Turing model. That's what we do in the paper, but let's not worry about that. Just think of number of bit operations in any reasonable bit complexity model. And the second problem I want to talk about is polynomial multiplication over finite fields. So this is a very similar problem, but it has some key differences, which we'll see later in this talk. So in this problem, I have polynomials of degree n, and I want to multiply them. And for this talk, I'm just going to work over a fixed finite field, fq, where q is a fixed prime power. And for measuring the complexity, again, I mean bit complexity, or you could use algebraic complexity. Since q is fixed, it doesn't really make much difference. Okay, so the earliest multiplication algorithms were the long multiplication algorithm, or it's also called the classical or schoolbook algorithm. And this goes back thousands of years. And this is a quadratic time algorithm. And the reason for this is basically you have to multiply every digit of the first number by every digit of the second number, and then add everything up. So that's quadratic time. Essentially, the same algorithm works for polynomials. You just multiply out the polynomials and add everything up. That gives you a quadratic time algorithm. Now, an interesting historical fact about this is that the famous Soviet mathematician, Andrei Kolmogorov, conjectured very explicitly that, that in fact, quadratic time is the best you can do. So can you see my cursor here? Am I able to point at things? I'm trying to point at this big theta. Yep, cool, okay. So the big theta means an asymptotic lower bound, so up to a constant. He conjectured that every multiplication algorithm has to be quadratic time. And you might wonder why such a smart guy like Kolmogorov would conjecture something that turned out to be so incredibly wrong. Well, Karatsuba wrote about this much later, and he said that probably the appearance of this conjecture is based on the fact that throughout the history of mankind, people have been using this quadratic time algorithm, and if a more economical method existed, it would have already been found. So this is basically the argument from ignorance. Not a very good argument, but this is maybe what he was thinking. Now, of course, he was wrong, and Karatsuba proved him wrong in 1962. And he came up with the first sub-quadratic algorithm for integer multiplication. And then there was a lot of work in the 60s, culminating in Knuth's result in 1969, which is sort of the best you can do using these kind of ideas. So in fact, this was not, I don't think he'd written the proof down anywhere. He gives it as a series of exercises in the Art of Computer Programming Volume 2. But you have to go back to an early edition to find this, which Drew actually found for me in the MIT library at some point. Thank you, Drew. And the exercises are actually quite tricky, but I did work through them and convinced myself that this is what Knuth got. So then, of course, Schönhage-Strassen applied the fast Fourier transform in 1971 to get this n log n log log n bound, and this is a very famous result and hung around for over 30 years until more recently, Martin Fourier, this is when I was a PhD student, improved the log log n factor, which was a great surprise to everyone, and got this k to the log star n. So log star n is the iterated logarithm. I won't give the definition, but it's a very, very slowly growing function. And then last year, Joris and I announced a clean n log n bound for this problem. So this is not published yet, but I can reveal that we've had some positive referee reports only in the last few weeks. So everything is looking pretty good. I should also mention Schönhage and Strassen in their 1971 paper, they conjectured that in fact n log n is the right bound. They felt that the log log n was somehow artificial and that n log n should be both an upper and lower bound, in fact. Now we don't know this lower bound. There are various things that point towards this lower bound, but I would say the evidence is still fairly weak. And we should bear in mind what happened to Kolmogorov's conjecture. So, you know, I mean, I would guess that it's correct, but, you know, I certainly wouldn't bet my house on it. Okay, here's a similar table of bounds for the finite field case. So I'm pretty sure that Schönhage and Strassen must have realized that their algorithm worked for polynomials over finite fields, but this doesn't seem to have been written down until 1977. Schönhage pointed out that you could do n log n log log n for polynomials over finite fields. When Fourier's algorithm came out, it wasn't clear that you could get this k to the log star n. And I wrote to him at the time and asked him about this, and he didn't have any ideas. So about a decade later, Joris and I and Grégoire Lasserre, we came up with another algorithm, which is a bit like Fourier's, a bit different, which did work for polynomials, and we were able to get this k to the log star n, where k is 8. And then more recently, Joris and I improved that to 4, and that was presented at the last ANTS in Wisconsin. And that is, to the best of my knowledge, currently the best known unconditional bound for this problem. Last year, Joris and I announced, we put out another paper simultaneously with our integer multiplication paper, where we announced an n log n bound for this case, but unfortunately, it's conditional on some conjectures about primes in arithmetic progressions. And I'll be speaking about that a bit later in the talk today. So the big unsolved problem in this area is, can you get this n log n unconditionally? And I'm hoping that maybe someone in the audience will see all this and cogitate on it and come up with something. We've been thinking about it for the last year or two and can't get anywhere with it. Okay, so here is the outline for the rest of the talk. I'm going to start by reminding you about discrete Fourier transforms and fast Fourier transforms over the complex numbers. Then I'll talk a bit about some some more advanced FFT techniques, including Rader's algorithm and Nussbaumer's algorithm, especially Nussbaumer's algorithm is very important for our main work. Then I'll give a sketch of the conditional n log n multiplication algorithm, which works for both integers and polynomials. And then finally, I'll talk about the unconditional n log n multiplication algorithm, which so far only works for integers. We don't know how to do it for polynomials. Okay, so DFTs and FFTs. So let me remind you what the discrete Fourier transform is. So we have a positive integer n. This is the transform length. And then we have this map from an n-dimensional vector space to an n-dimensional vector space. And I like to think of the domain of this DFT as the polynomials modulo this cyclic polynomial, x to the n minus 1. And what this map does is it evaluates a polynomial f at the n roots of unity on the unit circle, the nth roots of unity. Okay, so this is just a linear map. Here is an example of a length 4 DFT. So we take as input a polynomial of degree at most 3, and it spits out the values of that polynomial at the fourth roots of unity. So at 1 and I and minus 1 and minus I. Now you can see in this example that the naive algorithm to compute this DFT, if you just evaluate each of the entries separately, that's a quadratic time algorithm because you need to compute n things and each one is something like n operations to compute. And remember that these roots of unity, I mean, here they're fourth roots of unity, they're pretty easy to work with, but in general, they'll just be some arbitrary roots of unity with you know, dense looking bit representations as complex numbers. So you have to actually do some work. Okay, but of course, we can do better than n squared. So the simplest case is the power of 2 length Cooley-Tukey FFT. So you know, this is the one most commonly presented in textbooks, the decimation in time or decimation in frequency versions. So this reduces the complexity from n squared to n log n. And I've just got a little diagram here illustrating briefly how it works for a length 8 transform in the simplest case. So you start on the left with a polynomial modulo x to the 8 minus 1. And then at each level of this tree, you just split the modulus into its 2 factors in this balanced way. So first of all, you reduce f modulo x to the 4th minus 1 and modulo x to the 4th plus 1. And that's basically a linear time operation. That's sort of n operations to do that splitting. And then you split them again into these quadratic factors, and then you split them into the linear factors. And when you've split them into linear factors, what you've really done is evaluated f at the roots of unity. And so you can see this is n log n because each column in this diagram is linear time and the number of levels of the tree is log n. So that's an n log n algorithm. Now what's the point of this? Well, you can use discrete Fourier transforms to compute cyclic convolutions. And since I'm an algebra person, I prefer to think of a cyclic convolution as a multiplication in this ring, Cx modulo x to the n minus 1. So how does it work? Well, given 2 polynomials, f and g, what I do is first evaluate them at the n roots of unity. So that's this step 1. So that's using a discrete Fourier transform. Secondly, compute the pointwise products. So that means you're basically computing the values of the product of those polynomials at those endpoints. And in the third step, you run the discrete Fourier transform backwards to interpolate, to find a polynomial h that has those values at those endpoints. And it's easy to prove that the result you get is this product, f times g modulo x to the n minus 1. And the point is, if you have a fast way of computing this discrete Fourier transform, in other words, an FFT, then you get a fast convolution algorithm. And the reason this is relevant for integer multiplication is because integer multiplication is very much like convolution. So let me explain how that works. So I'll give you as an application of these ideas so far is the first Schönhage-Strassen multiplication algorithm. So they had 2 algorithms in their paper. The more famous one is the second one, which achieves the n log n log n bound. But I'm going to show you the first one, which is actually a lot easier to understand. This is the algorithm you would come up with if you were told, if you were given a homework assignment to come up with an integer multiplication algorithm based on the fast Fourier transform. This is really the right algorithm. But it's unfortunately slightly slower, as you'll see in a moment. So what do? You've got 2 integers, u and v. I'm going to rewrite them in base 2 to the b, and that means cut them up into chunks of b bits. So b here is chosen to be about log n, so it's exponentially smaller than n. And then you take these chunks and you encode them as polynomials. So they're coefficients of two polynomials with integer coefficients. So you can see that the degree is going to be something like n over log n, and the coefficient size is going to be something like log n. So these are very long, skinny polynomials, very high degree, very small coefficients. And I'm going to do a little running example in decimal because binary is too hard. So here I've chosen two random integers, u and v, and these are 9 digits long. And you should think of 9 as being a very, very large number. So these are very long integers, but I can't fit that on my screen, so I've just got 9 digits. And I'm going to cut them up into chunks of 3 digits. And you should think of 3 as being exponentially smaller than 9. So here I've got my two polynomials, f of x and g of x. And now what I'm going to do in step 2 is I'm going to multiply those polynomials. So I can multiply polynomials using FFTs, and I do this over the complex numbers. And the idea is I'm trying to get the exact product with integer coefficients, but since I can only work over the complex numbers, I have to do some numerical analysis. And you can show that if you work with a precision of some constant multiple of the coefficient size, which is log n bits, then in fact you get enough precision to be able to round the results to the correct integer at the end. So I'm not actually going to carry out the FFT in this example, but I'll just illustrate the product of the polynomials you get. So you multiply these two polynomials using FFTs, and you get this integer polynomial at the end. And then finally at the end, you just plug in, you just sort of undo the splitting step. You plug back in x equals 2 to the b, or in our example, x equals 1,000, and you get the result as an integer. And plugging in 1,000 is very easy. You see, you just sort of overlap these coefficients and add them up in the right way. So that's a linear time operation. So in fact, all of the work is in this step 2, is in the FFTs. Okay, so I hope that algorithm is clear. It's a very simple idea. I can give a very brief sketch of the complexity. It turns out that the complexity is dominated by the FFTs, which are of length n over log n. And then the question is, how do you do the coefficient multiplications? Because through the FFTs, you're constantly multiplying numbers by complex roots of unity. Now, when you do that, the way you have to think about it is these numbers are quite small, but of course, when n is big, these coefficients will eventually get quite large. Even log n gets large when n is big enough. So you have to worry about how do you multiply complex numbers with something like log n bits of precision. And it's very simple. What you do is you convert it to an integer multiplication problem by just scaling the decimal point or binary point or whatever it is. So it really becomes an integer multiplication problem. And so the cost of each coefficient operation is essentially m of log n. So you have to do these recursively. They will then get split into very small integers of size log n and so on. So when you work it all out, what you get is this recurrence for m of n. It turns out that you get n times m of log n in the second line. And then you can start unrolling the recursion. So at the next level of recursion, you get n log n times m of log n, and you just sort of keep unrolling it. So in the end, what you'll get is n log n, which is what they got for their second algorithm. But then you still also have log n and log n and so on. And you just need as many iterated logs as you need until you get down to the base case, until n is down to 1 or something. So from this discussion, I hope you can see why n log n is hard to get to. I mean, we're already at least a log factor away, and it seems like a very reasonable way to apply the FFT to integer multiplication. So we have to work quite a bit harder to get down to anything like n log n. Okay, so now I want to talk about some further FFT techniques. So first of all, one slide on Rader's algorithm. So this is from 1968, and this is kind of diametrically opposite the case I talked about before. So the Cooley-Tukey algorithm can handle the case of a power of 2 length, or more generally a smooth length. So what do you do in the opposite case where your length is a prime number p? You can't decompose it at all. So Rader shows how to reduce this problem to a convolution problem of length p minus 1. And when you're dealing with p minus 1, then you've got lots of options. P minus 1 might have small factors, or you could even just zero pad and work with a transform length that's twice as big and which has lots of smooth factors, lots of small factors. So there's lots of options once you've done this. So I just want to briefly explain how this reduction works. So I'll give an example for a length 5 transform. So here zeta is a fifth root of unity. So this is a complex fifth root of unity. And suppose we want to compute this discrete Fourier transform. So these 5 linear combinations of the input values. Now, if you stare at this for long enough, you'll notice that this is equivalent, more or less, to computing the length 4 cyclic convolution of these two sequences on the right. Now, you'll notice that the U's are indexed in a slightly funny order, U1, U2, U4, U3. And where I got that ordering from is I chose a multiplicative generator of the integers modulo 5. In this case, I chose 2, and I took the powers of 2. So I get U1, U2, that's U2 squared, that's U2 cubed. And then the same for the zetas, except running in the reverse order. Zeta to the 1, zeta squared, zeta to the 4th, zeta cubed. And if you look at, so if you take the convolution of these two sequences, you'll find that you'll get four values, and they turn out to be exactly these 4 linear combinations. Ignoring the U0 at the beginning of these 5 sums, you get these 4 linear combinations. So this is Rader's algorithm, and this works completely generally. For any prime p, you take your multiplicative generator, and this is what you get. So it reduces this length 5 discrete Fourier transform to a length 4 cyclic convolution. Okay, so we'll put that away for the moment. I'll come back to that later. And now I want to talk about Nussbaumer's algorithm. And so before so this will take a few slides, a bit more involved. Before I talk about Nussbaumer's algorithm, I need to tell you about multidimensional discrete Fourier transforms. So basically here the setup is we have a polynomial in several variables. So in this case, I've got an illustration of a 3-dimensional discrete Fourier transform where the lengths are 4, 5, and 6 in each direction. And so we represent this polynomial by, what is that? 6 is 120 coefficients arranged in this 3-dimensional grid. And the discrete Fourier transform in this case means that I want to evaluate this polynomial at the corresponding roots of unity. So x should be evaluated at the 4th roots of unity, and y at the 5th, and z at the 6th roots of unity. And so the input is 120 coefficients, and the output is 120 coefficients. Okay, so that's a multidimensional transform, and there is a standard method for computing one of these multidimensional transforms is that you can reduce it to one-dimensional transforms. And this is basically because the multidimensional DFT is basically a tensor product of the one-dimensional DFTs. But in terms of an algorithm, it's very simple. What you do is so in this first picture, I'm transforming my array in the x direction. So this gives me a bunch of one-dimensional transforms of length 4. And there are 30 of them, one for each slice going in that direction. And then I do the transforms with respect to y, and then I do the transforms with respect to z. And you can do these 3 steps in any order. They all commute with each other. So this is sorry, I'm getting tangled in my cord here. Okay. This is the standard algorithm. But Nussbaumer suggested a different method. It only works, it requires some divisibility conditions between the transform lengths. So I'm just going to do the simplest case, which is where all the dimensions are powers of 2. So here I've got a d-dimensional transform, so a polynomial in d variables, and the transform lengths are all powers of 2. And I've arranged them so that they're in increasing order. What I really need is that the last one, xd, has the highest order. So it's 2 to the k sub d. So basically his idea, I'm not going to go into the nitty-gritty details of this, but the basic idea is that first of all, you evaluate the first d minus 1 dimensions, but instead of evaluating them at the complex roots of unity, you evaluate them at the synthetic roots of unity using xd as a sort of placeholder for the root of unity of order 2 to the kd. And you do this by running the Cooley-Tukey algorithm, so the usual power of 2 FFT algorithm, but every time you're going to multiply by some complex root of unity, instead of doing that, you just multiply by that corresponding power of xd. And the point is that's very easy because that just involves relabeling coefficients, moving them around. You don't actually have to do any hard multiplication work. So once you've done that with the first d-1 variables, you're left with a bunch of polynomials in just that last variable, that placeholder variable xd. And then you have to actually do some work. So in the last dimension, you have to evaluate that last variable at the actual complex roots of unity. So there you have to actually do some complex multiplications. So basically what Nussbaumer is saying is you can delay all of the hard multiplication work until the last dimension. You can sort of shunt all the work into that last dimension. And this is really crucial for all of our new multiplication algorithms. So here is just a quick complexity analysis of what happens in Nussbaumer's algorithm. Let's suppose you're dealing with a d-dimensional transform. And let's say the total transform size is n. So that's basically the volume of that cube. So you can count the number of complex additions and multiplications that you need to perform. And in the standard algorithm, it just turns out to be n log n. It's the same as the one-dimensional case. For Nussbaumer's algorithm, the number of additions is the same. It's still n log n. But for the number of multiplications, and this is the really crucial thing, is we save a factor of d. Basically because we've eliminated all the multiplications from the first d-1 dimensions. We're only doing them in the last dimension. I'm assuming here that I've chosen all the dimensions to be roughly the same size. Okay, so this is the take-home message, is we've reduced the number of multiplications by a factor of O of d. And in the main algorithm, you'll see we get to choose d. And so we can basically save any constant factor that we want. Okay, so now I'm in a position that I can explain the conditional n log n multiplication algorithm, putting all these pieces together. So I'm going to sort of work through a numerical example to give you a bit more of a flavor of it. So I'm going to work with integers with 10 to the 14 bits. So that's 100 trillion bits, and it takes about 11 terabytes to store integers that big. So they're big. I mean, this is bigger than a number I can handle on my laptop, or it's sort of getting towards you sort of need a smallish cluster to handle something like this, I suppose. But it's certainly a practically sized integer multiplication problem. On the other hand, you'll see that it's really a little bit too small for this algorithm to work comfortably. So that's a bit of a downside. Anyway, so how does it work? I'm going to cut my integers into exponentially smaller chunks. So this is just like Schönhage-Strassen. So I'll cut them into tiny chunks of 46 bits, and I'm going to encode them as polynomials. And the degree is going to be about 2.2 trillion. So these are very, very long, skinny polynomials. And I'm going to multiply these polynomials in a very carefully constructed ring. In this ring, zt modulo t to the n minus 1. Now, what is n? N is this integer, which is, it's a product of, in this case, I've chosen 3 primes. These are very carefully chosen primes. You'll see how I chose them soon. But they're all roughly the cube root of n. And I need to choose them so that n is bigger than twice the degree, because I want to make sure that when I've computed the product in this ring, that I can recover the actual polynomial product. And I know its degree is going to be less than about, 4.3 trillion or something. So I've chosen these 3 primes, so their product is just a bit bigger than that, 5.5 trillion. Okay, so now I've reduced to this multiplication problem. Okay, the second step is I'm going to reduce, this whole algorithm is basically a series of reductions. So I'm giving you these reductions one at a time. So the second reduction is I'm going to use the Chinese remainder theorem to convert this one-dimensional cyclic convolution to a 3-dimensional cyclic convolution. So I'm transporting it to this ring on the right, z, x, y, z, modulo these cyclic things. So the mapping is very simple. I just take t to x, y, z. And I hope you can see that basically this amounts to permuting the coefficients in some interesting way. And just as a side note, in the Turing model, you have to worry about the cost of this rearrangement, which actually turns out to be, you can do it just in n log n time. So we've reduced to this 3-dimensional convolution problem now. So now in 3 variables. So it feels like we're sort of going backwards. Why do I want to reduce to a 3-dimensional convolution? But you'll see there's a reason. Okay, step 3, I've got this. So now I've got this 3-dimensional convolution problem, and I can reduce this to 3-dimensional discrete Fourier transforms. And this is just done the usual way, the same way as in Schönhage-Strassen. So first you compute the transform of both polynomials, then you multiply the coefficients, pointwise as complex numbers. These are just sort of small complex numbers now. And then you run the inverse transform to get the approximate product in this ring. But now we're working over C. We're doing this all numerically. And then we round the results to nearest integer. So you can do some numerical analysis, prove that again, the precision needs to be something like O of log n. So it's small. So the question is now, how do I do this step 1 and step 3? How do I do these discrete Fourier transforms in 3 dimensions? And this is where the plot thickens. What we're going to do is we're going to use Rader's trick to handle these 3-dimensional discrete Fourier transforms. This is a 3-dimensional version of Rader's trick. So it's pretty easy to generalize. I mean, I'm sort of using the fact that the multiplicative group of Z mod NZ decomposes as a product of these 3 subgroups of these sizes. This is more or less what it comes down to. So what's happened is I've reduced the problem to a convolution, but the transform lengths are 1 less. So we've gotten away from these prime lengths and we've gotten to these very nice lengths. And now you can see how I chose these primes. I chose them so that p minus 1 was divisible by a large power of 2. In this case, I chose them to be 15 times 2 to the 10. 2 to the 10 is about 1,000. So 15 times 2 to the 10, 18 times 2 to the 10, and 19 times 2 to the 10. Okay, so now I feel like I'm making some progress. So step 5 is I've got this 3-dimensional convolution with much nicer transform lengths. And now I use, I'll just say standard techniques because I don't have time to go into the details of this, but you can compute these sort of convolutions using, you can reduce them to smaller discrete Fourier transforms where the sizes are the factors of these sizes. So what we end up with is, first of all, some nice discrete Fourier transforms of size 2 to the 10 times 2 to the 10 times 2 to the 10. And this is really the whole point of all of the work that I've been doing, is I've been trying to get to this point where I can apply Nussbaumer's trick. And this is the situation where I can apply his trick, is where the transform lengths are all powers of 2 and all large, roughly equal powers of 2. And this is where we're going to win over previous algorithms such as Fourier's algorithm and Schönhage-Strassen and so on. So we're going to do those using Nussbaumer's trick, which means we only have to do all the complex multiplications in the last dimension. In the first 2 dimensions are just additions and subtractions. Only the last dimension is hard work. And then the other thing, unfortunately, is we get these annoying DFTs, the small ones, using these, where the transform lengths are, going back to the previous slide, are these leftover factors, 15, 18, 19, which I have very little control over. So I have to do these small transforms, 15 times 18 times 19. And I can do them using any method that I like. Okay, so that's an overview. And I now want to talk a bit about the complexity analysis. So firstly, d equals 3 is not big enough. We need the dimension to be a bit bigger than that. So one interesting thing is, in fact, d does not depend on n. You can choose n to be a constant. I think in the paper, our d is about 1 million. I'm sure that can be optimized, but I mean, it doesn't really matter. It's a constant. That's the important thing. Now, what turns out to be the hard bit in the complexity analysis is the cost of these annoying DFTs, these little tiny transforms of size 15 times 18 times 19 in our example. And the reason these are annoying is that we need to prove that these cofactors, these 15, 18, 19, are small. And that amounts to proving that there are small primes in arithmetic progressions of this type, p equals 1 mod 2 to the k. So this leads us onto some analytic number theory. So the main theorem along these lines is Linnick's theorem. So what Linnick proved is that if you have an arithmetic progression, p equals a mod m, which is supposed to contain primes, so a and m are relatively prime, then you can find a prime in that arithmetic progression with p less than m to the l. And L is some absolute constant. So it's a fixed, your bound is a fixed power of m, and a Linnick constant is an exponent that works. So currently, the best published Linnick constant that I'm aware of is 5.18, and I believe in Xylouris's thesis, which was not published, he got it down to 5. And I think there are actually even better results for smooth moduli, like powers of 2. You might get down to 2.4 or something like that. I'm not completely sure about that. But the trouble is that all of these bounds are hopeless, right? These analytic number theorists should be ashamed of themselves. Here's an example. Let's look at this progression. P equals 1 mod 2 to the 10. So 2 to the 10 is about 1,000. And here are the first few primes. And I just chose some of those small primes to get my example to work. But as you can see, there's, they come pretty thick and fast. They come about as fast as you would expect, just based on the stupidest heuristics about numbers being prime or not. The trouble is Linux theorem, what we can prove, it's only going to guarantee that that the smallest prime in this list is less than about 4 times 10 to the 15, which is just ridiculous. It's just huge. It's just embarrassing. Now, if you believe the generalized Riemann hypothesis, then in fact, you can take L to be anything bigger than 2. And this is still hopeless, right? We still get, here P is going to be about 1 million. Right, and that's still very, very large compared to these numbers you're seeing in this list. So these are terrible. But there is a widely believed conjecture is that, in fact, you can take any L bigger than 1. Any L bigger than 1 should be a Linux constant. And there are even stronger conjectures, which are, even less than a fixed power of M is what's believed to be the correct bound. But this is a long way from anything that anyone can prove. So here is what Joris and I proved. We proved the following. If there is a Linux constant less than this particular number, bigger than 1 plus 1 over 303, so that's about 1.003, I guess, then we can control these annoying discrete Fourier transforms, and we do get an n log n bound. So we can push that stuff out of the way, and it doesn't contribute asymptotically. Now, I'm sure we can improve, we can make that Linux constant bound a bit bigger. We can probably get something like, I don't know, 1 plus an eighth, maybe even 1 plus a quarter. But there's no way we can get anywhere up to 2. So even under generalized Riemann hypothesis, this doesn't work. So there's this annoying gap. There's this situation where what's believed to be true is much stronger than what we need, but what anyone can prove is much weaker than what we need. So we're in this sort of no man's zone. Yeah, we're in this terrible zone in the middle. Okay, so now I'll just very briefly say what happens for the finite field case. So basically the same algorithm works for multiplying polynomials over a finite field, but there are lots of additional technical issues you have to worry about, and I'll just briefly indicate what they are. So first you choose a bunch of primes, P1 up to PD, so this is for a suitably large dimension, and for a suitable power 2 to the k, depending on your n. And now the first thing that's a bit different is in the complex numbers, we have any roots of unity we want, but over finite fields we don't. We have to construct them. And so the first thing you do is in step 2 here, we construct an extension of FQ, which contains the roots of unity we need. And you can already see here, this is a very non-algebraic algorithm, okay? Okay, and the third step then is we have to reduce our problem to multiplication over this extension field. So that means we have to cut things up into chunks of S coefficients and repackage them together. So now we've got a multiplication problem over this larger field. Okay, now we proceed the same way as in the integer case. So we convert it to a multi-dimensional convolution problem, and then we reduce to discrete Fourier transforms over our field. And then we use Rader's trick to reduce the transform length by 1 in each dimension. And then we apply Nussbaumer to handle the large powers of 2 and so on. And so basically the algorithm is the same after that. And I'll just mention in characteristic 2, there are 2 issues. One is the obvious one, which is you can't use power of 2 transforms anymore, but that's easy to fix. You can just use power of 3 transforms. There's one other issue, which actually even took us a while to notice that there was a problem, is that this p minus 1 is always even. So when you apply Rader's trick, you necessarily introduce these annoying sort of x squared minus 1 factors. And so you have to work a bit harder to deal with that, but it turns out you can. So that problem is okay. Okay, and here is the theorem we proved for the finite field case. If there is a Linux constant less than 1 plus this ludicrously small number, 2 to the power of minus 1,162, which is small, but it is positive, then we get n log n for multiplication. And so we probably can improve this constant, but we don't know how much we can improve it by. Maybe you could get, I don't know, 2 to the minus 100, or maybe 2 to the minus 10. I really don't know. We haven't really tried to optimize that because we're surely still so far away from what is provable anyway. But the reason this constant is so much worse is basically because of these technical issues that I mentioned on this previous slide. Yeah, there's various reasons. You need these primes to have various properties that anyway. So that's currently the situation for polynomial multiplication. We would love to be able to improve this result, especially to make it unconditional. Okay, so now let me tell you about the unconditional n log n multiplication algorithm. So this is the one that seems to have generated the most interest. Okay, so again, I'm gonna run through an example. So I'm going to take the same n as before. So we're multiplying integers with 10 to the 14 bits. And as before, I'm going to cut them up into small chunks of 46 bits. And so now we're dealing with polynomials of degree 2.2 trillion. And I'm going to do the same thing as before, but with 3 different primes. I'm not going to choose my primes in arithmetic progressions. I'm going to choose my primes to be slightly smaller than a power of 2. And in this case, they're all going to be just below 2 to the 14. And from a theoretical point of view, this is great because it's easy to prove that there are primes that are close enough to a power of 2. We don't have to worry about arithmetic progressions, so we don't get involved with Linux theorem or GRH or anything like that. I mean, there are technical things. We need it to be close to a power of 2, but not too close to the power of 2. But it turns out that you just use the prime number theorem with a very standard error bound, and it all works out fine. Okay, so what are we going to do? Same as before. We're going to reduce to multiplication modulo t to the n minus 1, where n is this product of these 3 primes, which turns out we got lucky in this case. We got very close to 2.2 trillion. Sorry, 4.4 trillion. It's just a bit bigger than 2 times the degree, so that's good. And then we do the same as before. We reduce to 3-dimensional convolution and then to 3-dimensional discrete Fourier transform. So this is where we are at the moment. We've reduced to this problem of computing DFTs of these funny prime sizes, slightly less than a power of 2. But now I'm not going to use Rader's algorithm. I can't use Rader's algorithm because I don't know anything about p minus 1. I haven't said anything about the factors of p minus 1. I'm going to do something different. I'm going to use this thing we've introduced called Gaussian resampling. And what this does, it does something that seems kind of unbelievable at first. It reduces this 3-dimensional discrete Fourier transform problem with prime lengths it reduces it directly to computing a discrete Fourier transform of slightly larger power of 2 lengths. Now, you might think this is completely crazy because this discrete Fourier transform on the left, it's all in terms of these roots of unity of order P1, P2, and P3. It seems to have nothing to do with a discrete Fourier transform of order 2 to the 14. But I'm going to show you how you do it. Once you've done that reduction, then it's easy. Then we're back in the situation where we can use Nussbaumer's algorithm. This is the name of the game. We're constantly trying to reduce to this situation where we can apply Nussbaumer's algorithm. So that's the point of this Gaussian resampling, which I'm now going to explain. So instead of doing this big, complicated 3-dimensional version, I'm going to do a very small 1-dimensional version, but the same idea works in d dimensions. So suppose we're in the following situation. Suppose we want to compute a DFT of length 13. So we have an input vector of length 13, and we want to compute its transform u hat, which is also of length 13. So this is with respect to the 13th roots of unity in the complex numbers. But suppose we're really stupid and we only know how to compute DFTs of length 16. And I want to use my DFT of length 16 to help me compute a DFT of length 13. Okay. So what I'm going to do is I'm going to introduce this linear map, which I'm going to call a resampling map, which goes from C13 to C16. And it's sort of trying to somehow turn my sequence of length 13 into a sequence of length 16 in some nice way. And I'm going to show how to construct S over the next few slides. So this diagram is showing a typical input vector of length 13. Now, the x-axis is just the index, and then the y-axis is the actual value of u. So this is u0, this is u1. I'm just graphing this function ui. And I've divided up the unit interval into 13 equal segments. And you can see that it's actually joined at the 2 ends, right? So this point here on the left, u0, is actually the same as, in effect, is the same as u13, because this is really r mod z. Okay, so this is my input vector u. So what am I going to do? I'm going to draw a Gaussian curve at each point, which goes through this point. So it has height ui, and the width is going to be proportional to 1 over 13. So a Gaussian curve on each point. And then I'm going to add all these Gaussians up. It gives me some smooth function, f of x. And you can see this function is sort of trying to interpolate these points. Okay, so it's sort of trying to head towards these points down here, for example. And then it's trying to head up to this point. It doesn't actually succeed, but it tries to. And then I'm simply going to evaluate this function at the 16th division points. Okay, so this is a linear map, and it's sort of resampling the sequence. It tries to smooth out the sequence and then resample it. Here is a matrix of this map, going from C13 to C16. And if I look at, for instance, this middle column, you can see that it has this big entry in the center, and then it decays quite rapidly, like a Gaussian off to the side as I go up and down. And then these blank entries, they're not really zero, they're just entries that are numerically insignificant. I guess at three decimal places, you don't see anything. So I've just left them out. Okay, but this is not a square matrix. It's a 16 by 13 matrix, and it has this sort of diagonal running at a slope of 16 over 13 down the middle. And you can see from this picture that each output coordinate depends mainly on the nearby input coordinates. Okay, now I'm going to tell you a few interesting facts about this resampling map. So the first thing is there's this very nice commutative diagram. If I start on the top left with my vector u, so this, remember, is length 13. So on the one hand, I could go across and compute the discrete Fourier transform of length 13 to give me u hat. In the other direction, I could resample it to length 16 using the procedure I just described, and then compute the discrete Fourier transform of length 16. Now, what turns out to happen is that there is a simple relation between u hat and v hat, and it comes from the fact that the transform of a Gaussian is a Gaussian. So this is now of a continuous. This is now doing continuous Fourier analysis. The transform of Gaussian is a Gaussian, and you can use that to prove in half a page of algebra that v hat is actually a resampled version of u hat. This is really key. And so this map s hat is basically the same as s, except for some scaling factor and some permuting the coefficients around. So it basically has a matrix of the same form. Okay, so that's the first thing. The second thing is that we can compute this resampling map efficiently, and that's because the Gaussians decay so rapidly. And what turns out to happen is that you can compute it in t times square root of log t operations. And this should be compared to the cost of the FFT, which is t log t. So it's asymptotically negligible by a factor of square root of log t compared to the FFT. And the last thing, which is perhaps the least obvious thing, is that you can run it backwards. There's a deconvolution algorithm which lets you undo the effect of this resampling. Now, we don't actually prove this in the paper. We do something a bit different because it turns out to be technically simpler, but I'm pretty sure this is true. So you can run it backwards, and you can recover the u from the v. So here's the algorithm. Very simple. You start with u. I want to compute this transform length 13. So what do? I resample it to length 16. That's fast. That's asymptotically 0. Then I compute the DFT of length 16, which I know how to do. And then I run the deconvolution algorithm, which is also fast. And so I've computed this length 13 transform entirely by using a length 16 transform. All right. So if I combine that with everything else I said before, and I have to work out a multi-dimensional version of this Gaussian resampling, and then I do everything that I said before, then this is how we get our n log n down. So I'll finish off by reminding you of the big unsolved problem, which is the finite field case. Can we get this n log n unconditionally? And unfortunately, we don't know how to do Gaussian resampling over a finite field. There's just no good analog of the Gaussian function. We're using the Archimedean property in many places all over the algorithm. So, we might ask, is there some other way of changing the transform length over FQ? So I've given you two methods. I've given you the Gaussian resampling, which doesn't seem to work over finite fields, and the other method was Rader's algorithm. Let's just change the transform length. But unfortunately, Rader's algorithm seems to require that we know primes in arithmetic progressions. So those are the only two real methods I know, and we haven't been able to come up with anything else. So that's I think the problem that needs to be solved in order to get an n log n multiplication algorithm for the polynomial case. All right, I'll stop there. Thank you very much.
Thank you, David, for absolutely superb talk. So I'm sure everyone else is giving virtual applause.